Hello. In the previous video, we introduced this Newton's law of gravitation. We understand it's the attraction force between those two objects that's divided with a distance of r, and that attraction force is going to be equal to gm1 times m2 divided by r squared, g being a constant value. It's universal gravitational constant. And we use the example of the Earth and you, and we figure out that force is essentially equal to our weight equal to 9.8 times mass of us, right? And 9.8 is basically our G. So understand how that 9.8 number is derived. Now, today I'm going to look at some other examples. So today we're going to take giant leap of faith. We're going to go from Earth to Moon today. So this is going to be our Moon. And then imagine you have a vehicle right there, and this vehicle, it's on the Moon. Okay. So this exploration vehicle has a mass of 250 kilograms. Okay. And the mass, no matter if you're on Earth or on the Moon or on the Mars, they all have the same mass because it's amount of matter, right? However, the weight is different. So the mass stays the same, but they told us what's gonna be the weight of this vehicle on the Moon. So be aware the G here would not be 9.8 anymore on the Moon. It's going to be actually 1/6 of it. So it's 1.6 meter per second square. It's the acceleration unit, right? Why this G is different? Because if you go back to this fundamental formula, this big G, it's universal. That will be the same. However, I'm going to use blue to highlight what's different. This will be different, right? Because that's going to be changed from mass of the Earth to mass of the Moon, and they are not the same mass. And this will be different because this will be changed from radius of Earth to radius of the Moon. So because of this two variable has changed, when you put those new values in, you are going to get a G. You are going to get to that value to be 1.6. Okay. So for this problem, they want us to find what's going to be the weight, what's going to be attraction, gravitational pull on the Moon. That will be 250 mass times G, Moon, times 1.6. And that will give us a value of 400 Newton. Okay. So that's the first example, fairly easy. And through this example, you understand the mass stays the same no matter where we are. However, the gravitational pull is different. And why it's different? Because of here. Okay. Now, let's look at something different. Imagine you are an astronaut and you are in the space shuttle orbiting the Earth. So this is our blue planet. This is our Earth. And you are in the space shuttle right here, flying and orbiting around it. Yeah, orbiting around our Earth. And this altitude is about 250 kilometer high. Okay, so this distance right here is about 250 kilometer. And you this astronaut in the space shuttle is going to have a mass of 70 kilograms. Then we want to find what's going to be the weight at this position at 250 kilometers off from Earth. So normally, thinking about this problem, normally we know the weight is equal to mass times G. And the mass is given 70, G is 9.8. But can we use 9.8? Because 9.8 is derived from this Newton's law of gravitation, And in this formula, what's going to be the distance between those two objects? It's when we are standing here on the surface. However, the radius now has been 250 kilometers more, right? It's further away from the center of the Earth. So what do you realize? This r has increased. When r, the distance between them increased, what happened? When r increased, your force, attraction force, decreased. Knowing that, we know this g is no longer 9.8. So make a note that's not 9.8 anymore. We are going to figure out this customized g, right? So that's where we're going. So we go back to this original equation. We realize this doesn't work anymore for this problem because it's not on the surface of the Earth. And so we're going to use this original equation. All right, in this original equation, let's go back to our g. G is a constant. We don't need to remember this one. I'm just copy down. And the mass of the Earth, that's also a constant. No need to remember. Just need to know where to find it. That's mass of the Earth. And then we're going to have the mass of the astronaut, which is 70 kilograms for this problem, right? Then the distance between the Earth and the space shuttle where the astronaut is at, and it's going to be this is going to be our r, and that r is going to be the radius of the Earth plus 250. Okay, the radius of the Earth is 6378 times 10 to the power 3, that's meter, and it's 250 kilometer above, change kilometer to meter. So we're going to times 10 to the power 3 times 1000, and that's the real true distance between them, and that's squared up. Then go ahead and pause the video, see what you got for this. And I actually encourage you to only solve this because this is a mass. I want you to find this g. What's this g value equal to? And pause the video, see what you have. Okay, now you are back. And what's the value you got for this blue blob? It's a 9.07. As you predicted, this g is going to be less than 9.8. And then times our mass. So it's 9.08 times 70 kilogram, and that will be 635 Newton. That's how much the gravitational pull by Earth to this astronaut who is orbiting 250 kilometers above. And that pull is less, right, than as opposed to the astronaut standing on the Earth. All right, so hopefully you have a great understanding about this Newton's law of gravitation. Okay, I'll see you at the next video. Bye now.